In this video, I want to introduce the idea of system calls that are necessary for process control. So first of all, what is a process? A process is basically a running program. So by default, I have, for example, a file on my desktop, and I know I could click on it, I could run it. Initially, it's just a file though, right? Only once I click on it, once it's up on my screen, is it actually running, and that's what we'll call a process, right? And we're going to actually spend a lot of time talking about what a process is later on in the course, but for now, I just imagine it's a running program. All right, so processes have all sorts of components to them. They have, for example, the program's code, the program's data, its current state, right? What resources have been allocated to it, so on and so forth, right? I need to know all these things in order to basically have a program running. It's also going to have some attributes associated with it, right? So who owns it, who's running it, how much memory is it allowed to have, right? Is it going to be terminated at a certain point? All those sorts of information I'm going to know. All right, so so these basically are running programs, right? I don't want anybody basically to be able to mess with them, right? Unless they're allowed to, right? So a program that's running, right, should be kind of kept safe in a sense, right? So it's permitted to do certain things, and then it's not permitted to do other things. Typically, you're allowed to do things like, for example, create other processes. So if I have something that's running, I can maybe run another program from it. Makes sense. I can have what is called a child process. Probably though, what I don't want to have it do is do things like kill off another process. So I don't want it to basically shut down something that's already running. Okay, so there's this notion, right, of privileges that a process can have or not have, right? And somebody needs to watchdog that, right? Somebody needs to guard that. That's why these things are typically implemented as system calls, because the operating system will actually know, oh, it's okay for you to create this, or okay, it's okay, or it's not okay for you to delete this thing, right? Those are the type of things that the operating system will basically be able to enforce. It'll be able to know who's allowed to do what. All right. And then the big thing, of course, right, is that basically our processes that are running programs are going to want different resources. So they want different RAM, they want different CPU time. Who is going to be in charge of metering out those resources? It's going to be the OS, right? When I have limited resources, somebody needs to be in charge of them. Generally, it's going to be the operating system. And the operating system, right, is going to basically provide these different calls that a program can make to request things, right? So I do things like, for example, do maybe a malloc, right, which could go to an operating system and say, hey, I need to have this, I need to request this amount of memory. Okay? And the operating system maybe can meter it out, right? I don't want to just have everybody be able to go and grab whatever they want in main memory. I want them to all go through the operating system to do it. Okay, so those are again going to be system calls, right? All these are system calls that basically support a program's execution, right? So give me the resources, controlling what it can or cannot do. Another thing that the operating system basically is going to do is have support for basically concurrency, or running multiple programs at the same time. So let's take a look at some diagrams here. So what I have here is basically memory layouts for DOS, MS-DOS, and then BSD. So what is this? Okay, so first of all, MS-DOS is an operating system. So earlier in a previous video, I brought up a command line interface, and I showed you guys on Windows what it looks like to navigate through a system using a text-based interface. Back in the old days, basically that's all we had. All the people that came before me, this is even before my time, right? I think those people had, right, were text-based interfaces. So DOS is an example. So DOS is basically a system where all I had is that command line interface, okay? So in that kind of environment, I was only allowed to do one thing at a time. I had basically one screen, right, with one program running. So let's think for a second, how might maybe the main memory of the system look when it's running? It would look something like this. Okay, so I have this little diagram here, and you can imagine, right, that I'm running, and so there's basically some little kernel, right? So this is the kernel that provides a system call API that everybody can use, right? Sounds good. And then on top of that, there's that command interpreter, right? So we talked about parsing the commands, dir, cd, and doing things based on that. Okay, sounds good. Then we have some free memory, okay? So if I want to talk about system memory, RAM, right, in these old systems, this is how it look, right? I have my kernel, my command interpreter, some free space. Okay. So let's say I want to run a process, right? This is obviously going to be something that's under the control of my operating system, right? So normally, right, I'm running my OS, right? The shell interpreter is up, right? I'm typing commands. Then all of a sudden, I want to run something. What happens? Well, what will happen in DOS, right, is basically you copy your program to memory, right? So there's only one program here, right? That's what makes it easy. We basically copy our process, right, our program, right, from being a file on a disk to actually being something that's running on the computer right now. So we make a copy of something. Now, when we do this in DOS, we actually do something a little bit interesting, which is, notice we kind of shrink this over here. Think maybe for 1 second, why might we shrink the command interpreter? Well, the simple reason there is that we don't have a whole lot of memory, right? So in older systems, we have like 640 KB of RAM. We don't have unlimited space, so if we want to load a large program, we're going to have to unload stuff. since we have only a single task environment, it makes sense that maybe I could shrink or even remove that command interpreter because, well, I'm already doing the one thing that I want to do, so do I really need it or not? Probably not. All right, so this is kind of the most simplest thing you could have for an operating system, right? This is an operating system that has only a single task at a time, right? So it's running normally that command interpreter, then it switches over, right, to running a process whenever I go to run a specific command. All right, so this is something that OS will manage, and we'll actually talk about in more detail later on. All right, so here's a different example. This is BSD. This is an environment that supports multitasking, right, versus single task over here. So this is a little bit different because whenever we run a program, we need to figure out where it goes, right? And this is, again, going to be something that has a system called behind the scenes because the OS is the only one that knows the layout of all of the memory and kind of pick where should somebody end up, okay? So my program maybe is going to run, it's going to make a request, oh, I need this much memory. The OS will see that request and pick where it goes. Okay, and so our memory allocation looks a little bit different, right? So here I have my kernel down here, and then I have different programs. So I have programs B, C, and D all running, and of course there's an interpreter as well. And my OS is going to be in charge, right, of where those things go, right? They're not going to be back-to-back per se, right, in this specific order. It's going to be wherever the OS wants to pick them. And there's also our free space, right? Our free space is a little bit smaller now. Here, right, we're also introducing the idea of a background task and a foreground task. So if I'm running a program, right, if I'm interacting with it directly, like for example, I'm interacting with process C, this would be my foreground task. Foreground, I'm writing over stuff that I shouldn't be writing over. Versus other things, D and B are background tasks. So background. My handwriting is degrading. As I go through more videos in one session, my handwriting gets worse over time. Maybe it's always, but I don't know. All right, so those are background tasks versus I have a foreground task. And I have my free memory over there, and my interpreter is just somewhere else. Okay, so this is more kind of typical of what you'd see in modern operating systems. As a quick question for you guys before we move on, how abstract is this image, right? So how close to reality is this, or how far from reality is this? Is this really how a system would look? Take 1 second and think about that. So this is pretty abstract. It's pretty abstract because all my free memory is in one place, and that's awfully convenient. Normally, you have some sort of level of fragmentation where it's going to be like, oh, there's some free space here, free space here, free space there, and it's all in one piece. So that's kind of the giveaway here. This is very abstract, right? This isn't how it works in practice. All right, so hopefully, right, you guys have a little bit of a sense of basically what a process is now and how an operating system has to manage them, right? There's certain permissions they're supposed to have, right? And then the operating system has to manage basically loading them into memory, switching between them, that type of thing, right? I have sort of a sense of a single task and then a multitask environment. All right, so that's all I got for you guys. I'll see you in the next video.